If an electrical installation is designed according to the National Electrical Code, often abbreviated as NEC, and steel wire or tape, often abbreviated as SW or TW, armored cables are used. It satisfies the NEC grounding requirements. The relevant code section is NEC Article 250.118(3), which states that metal-clad cable shall be permitted to be used as a grounding means where continuous maintenance of its metallic covering is assured. Steel wire or tape armored cables have similar grounding performance to other metallic jacketed cables commonly used in North America, such as metal-clad cables, often abbreviated as MC. Both types of cables provide a low resistance path for ground fault currents, enabling proper operation of protective devices and ensuring the safety of the installation. The steel wire or tape armor provides a metallic pathway for ground fault currents, allowing them to be safely diverted to the electrical panel's grounding system. The armoring also offers protection against physical damage and helps maintain the integrity of the electrical circuit. Steel wire or tape armored cables do not typically exhibit higher resistance than other types of metallic jacketed cables. The resistance of electrical cables depends on the material, cross-sectional area, and length. Proper selection of steel wire or tape cables with appropriate amperage ratings ensures adequate current carrying capacity and minimal voltage drop. Using steel wire or tape armored cables in an electrical installation that complies with the NEC satisfies the NEC grounding requirements. These cables offer comparable grounding performance to other metallic jacketed cables commonly used in North America and provide a low resistance path for ground fault currents, ensuring the safety of the installation. Electrical grounding is a critical aspect of electrical safety, ensuring that electrical systems are properly connected to the earth to prevent electric shock hazards and equipment damage. The National Electrical Code, which is the NEC, provides comprehensive guidelines and standards for electrical installations in the United States, including requirements for grounding electrical systems. Grounding serves several important purposes in electrical systems. Firstly, it provides a low impedance path for fault currents to flow back to the source, allowing protective devices such as circuit breakers or fuses to quickly disconnect the circuit in the event of a fault. This helps to prevent electrical shocks and minimize the risk of fire or equipment damage. Secondly, grounding helps to stabilize voltage levels in the electrical system, reducing voltage fluctuations and ensuring proper operation of equipment. Thirdly, grounding provides a reference point for electrical potential, minimizing the risk of static electricity buildup and discharge. The NEC outlines specific requirements for grounding different types of electrical systems and equipment. These requirements are based on factors such as the voltage level, type of wiring system, and the environment in which the electrical system is installed. One of the key principles of NEC grounding is the concept of bonding, which involves connecting all non-current carrying metal parts of an electrical system together to create a continuous, low-impedance path to ground. This includes metal conduits, enclosures, equipment frames, and other metal components. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock if a fault occurs. Another important aspect of NEC grounding is the use of grounding electrodes, which are conductive objects that are buried in the earth to provide a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the minimum size and type of grounding electrodes that must be used, as well as the methods for installing and connecting them to the electrical system. In addition to grounding electrodes, the NEC also requires the use of grounding conductors, which are wires that connect the electrical system to the grounding electrode. Grounding conductors must be sized appropriately to carry the maximum fault current that could occur in the system. The NEC provides tables and guidelines for determining the appropriate size of grounding conductors based on the size of the circuit conductors and the type of electrical system. When using steel wire or tape armored cables, it's important to ensure that the armor is properly grounded according to NEC requirements. The armor of the cable can serve as a grounding conductor, providing a low impedance path for fault currents. However, it's important to verify that the armor is properly connected to the grounding system at both ends of the cable run. This typically involves using bonding connectors or clamps to securely attach the armor to metal enclosures or equipment frames. In addition to the general grounding requirements outlined in the NEC, there are also specific requirements for grounding certain types of equipment and systems. For example, the NEC provides detailed guidelines for grounding electrical services, which are the main connections between the utility power grid and the building's electrical system. The NEC also includes requirements for grounding separately derived systems, such as generators and transformers, which supply power to specific areas or equipment within a building. It's important to consult the NEC and other relevant standards to ensure that all electrical systems and equipment are properly grounded according to code requirements. Failure to properly ground electrical systems can result in serious safety hazards, including electric shock, fire, and equipment damage. The NEC also addresses the grounding of sensitive electronic equipment, which may be susceptible to damage from voltage surges or electrical noise. The NEC recommends the use of dedicated grounding systems for sensitive electronic equipment, such as computers, medical equipment, and audio/video systems. These dedicated grounding systems provide a clean, low-impedance path to ground, minimizing the risk of damage from electrical disturbances. In addition to grounding, the NEC also addresses the issue of overcurrent protection, which is the use of circuit breakers or fuses to protect electrical circuits from excessive current flow. Overcurrent protection devices are designed to interrupt the flow of current in a circuit if the current exceeds a predetermined level, preventing overheating, fire, and equipment damage. The NEC specifies the types and sizes of overcurrent protection devices that must be used in different electrical circuits, as well as the methods for installing and maintaining them. It's important to choose overcurrent protection devices that are properly sized for the circuit they are protecting. If the overcurrent protection device is too small, it may trip unnecessarily, causing nuisance outages. If the overcurrent protection device is too large, it may not trip quickly enough to protect the circuit from damage. The NEC also addresses the issue of arc fault circuit interrupters, often abbreviated as FSIs, which are special types of circuit breakers that are designed to detect and interrupt arc faults. Arc faults are dangerous electrical conditions that can occur when electricity jumps between two conductors, creating a high-temperature arc that can ignite nearby materials. FSIs are required in many areas of the home, including bedrooms, living rooms, and dining rooms, to protect against arc fault hazards. The NEC also includes requirements for ground fault circuit interrupters, often abbreviated as GFCIs, which are special types of receptacles or circuit breakers that are designed to protect against ground faults. Ground faults occur when electricity leaks from a circuit to ground, posing a risk of electric shock. GFCIs are required in wet or damp locations, such as bathrooms, kitchens, and outdoor areas, to protect against ground fault hazards. In addition to the technical requirements for grounding and overcurrent protection, the NEC also addresses the administrative aspects of electrical installations. The NEC requires that all electrical work be performed by qualified and licensed electricians who have the knowledge and experience to safely install and maintain electrical systems. The NEC also requires that electrical installations be inspected and approved by a qualified electrical inspector, who ensures that the work complies with the NEC and other applicable codes and standards. It's important to choose a qualified and licensed electrician to perform electrical work, as they have the training and expertise to ensure that the work is done safely and correctly. A qualified electrician will be familiar with the NEC and other relevant codes and standards, and will be able to design and install electrical systems that meet all applicable requirements. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It's important to stay up to date on the latest version of the NEC to ensure that electrical installations comply with current code requirements. Many states and local jurisdictions adopt the NEC as their electrical code, so it's important to check with the local authorities to determine which version of the NEC is in effect in a particular area. The NEC is a comprehensive and complex document, so it's important to consult with a qualified electrician or electrical engineer if you have any questions about electrical installations or code requirements. An electrician or electrical engineer can provide expert guidance and assistance to ensure that electrical systems are designed and installed safely and in compliance with all applicable codes and standards.